Hi guys, okay, question 7 for HL, 12 for SL. This is definitely the hardest question we've come across yet for SL, and I'd say probably for HL as well. It actually took me a while to figure this question out. So the area of, this is the cover of a box, it is A centimeters squared. Find A in terms of P and Q, right? So this part was okay actually, A part I. So the area is the area of this triangle plus this rectangle plus this triangle. You could do it as just one big triangle if you want to, because you know this has to be, because this is a rectangle, it tells you this is a rectangle. This is 6 and this is 8. So you could just say the area is P plus 6 times 8 plus Q. Or you can say it's the area of this triangle, which is a half 8 times P, or a half 8P if you like. Because remember guys, because this is a rectangle, this is a right angle, then this is a right angle, which means this is a right angle. So that's a right angle triangle. Similarly, this is a right angle triangle. And this is a right angle triangle. Another thing to note guys is because this is a straight line, this is parallel to this. This line here is parallel to this line here. This angle is the same as this angle, and this angle is the same as this angle. So that's actually that was the hard part of this question. But anyway, first part's okay. A half 8 times P plus, let's do the other triangle, a half 6 times Q, 6 times Q plus 6 times 8 for the rectangle, which is 48, and that's equal to 4P plus 3Q plus 48. Fine. Part 2. Show that A is equal to this. So basically now he wants to find A in terms of Q only, but we have a P in there. So how do we find A in terms of P only? Well, we need to find a way of getting Q in terms of P, or sorry, P in terms of Q. We need to find a way to write P in terms of Q. So we basically need another equation. We need another equation with just a P and a Q in it. Now, there's two ways, and this was the hard part of this question for sure. There's two ways to do it. You could see that there are similar triangles here, that this triangle here is similar to this big triangle here. So you can say the red triangle is similar to this triangle because this line here is parallel with this line. So this angle is the same in both of them. This angle is the same in both of them. And this angle is the same in both of them. And then because they're similar, you can say 8 over P is the same as 8 plus Q over 6 plus P. So this side over this side in the red triangle is equal to this side, 8 plus Q, over this side, which is 6 plus P. Or, and I'm still debating which one to use for you guys, to show you guys. I think I'm probably going to go with the second method, but anyway, you could try both methods, it's fine. I can say that the tan of this angle here is equal to the tan of this angle here. That'll get me an equation with P and Q in it. So I can say the tan of, let's call this angle here X. So let this be X, and let this is then X. So tan X equals 8 over P, and tan X also equals Q over 6. So opposite over adjacent is 8 over P, and here opposite over adjacent is Q over 6. Therefore, 8 over P equals Q over 6, because if tan of X is this and tan of X is that, then this equals that. Multiply across, and I can get, well, I wanted P in terms of Q, so I'm going to multiply across here, and I'm going to get P is equal to multiply across, I get 48, and then divide across, I get Q. So P is equal to 48 over Q. Then, I'll just do a line here, guys, so it's all on the one page. Then I have my area, this area here. Hang on, let me do this. Hang on. Now I have my area is equal to 4P, but instead of P, I'm putting this 4P, but my P is now 48 over Q. 4P plus 3Q plus 48, nearly what they want. This is equal to 192. 4 times 48 is 192 over Q plus 3Q plus 48. That's what they wanted me to show. Done. QED. Then he says find dA dQ. Okay, dA dQ. Well, let's move down here, guys. So this is A. So this is part B. So B, A is equal to 192 over Q plus 3Q plus 48. But I'm actually going to write this as 192 Q to the minus 1. Because remember, when we differentiate, we want this in terms of, we want it in index form. So 192 Q to the minus 1 plus 3Q plus 48. So dA dQ is equal to, multiply by the power, minus 192 Q to the power of negative 2, subtract 1 from the power, plus the derivative of 3Q is just 3, and then this is 0. So that is actually, that is dA dQ. Great. Part C. So Ellis wishes to find the value of QU, the value of Q that will minimize the area of the top of the gift box. Write down an equation Ellis could solve to find this value of Q. So the equation, if you remember, guys, how do we find the maximum or the minimum, or how do we optimize? It's where the derivative equals 0. So that's simply all they want you to write down here is the equation that he could solve is basically dA dQ equals 0, or minus 192 Q to the minus 2. By the way, this is also over Q squared. That's the same thing. Either is fine for this question, equals 0. And then finally, CII, it says hence or otherwise find this value of Q. So he's basically saying solve that equation to find Q. Now, yes, you could solve it for sure. Let's do that right now. I can, well, let me show you how to do it by hand. So I can say 192 over Q squared equals 3. So that's just adding this to the other side. Q squared is equal to this divided by 3, which would be 64. And then Q is equal to 8. It has to be a positive value because obviously Q is a length, so it has to be a positive value. Now the other way we could solve this is we could put this into and solve. So I could do menu, algebra, numerical solve, negative 192 over, let me do this, over Q, I can use Q squared, plus 3 equals 0, comma Q, and I get 8, so it gives me the answer there. Or the other way I could do it, because it says hence or otherwise, I could actually graph A, and it's worth, let me just delete this, it's worth noting what I'm going to do here, but I'm going to sketch this, so not even the derivative, I'm just going to sketch this function here, which is the area function. 192 over, again guys, I'm using X because 192 q to the minus 1 is 192 over x. Or I could even just do it. I could do times x to the power of negative 1 if I wanted. Plus 3x plus 48. Now if I actually sketch this, and if I zoom, let's zoom out a bit, see what's going on here. Okay, so all these values here are for negative q's. Now q is a length, so these don't matter. What's important is these values here, because this is when q, or x in this case, but this is our length q, is positive. Now we need to find the value of q that minimizes this, because this is our area function. Well, the value happens at this minimum here, which is, guess what, 8. So it's at 896. And this is actually a nice way if it said, what is the area? It doesn't ask us in this question, just says find the value of q. But if it then said, what is the area? Well, that's a nice easy way to do it. You just put it into the graph. So definitely valuable. And I've mentioned this in previous, well, in my optimization lesson, I've said, you can do it this way, but the question, and this is a perfect example of a question that does it, can force you into doing it the derivative way. It actually tells you find the derivative. Then it even says write down an equation Ellis could solve to find this value of q. So that's like forcing you to know that the derivative is where the derivative equals 0, and then you get q equals 8. So either way, that's the answer. Okay, one more question to go for us all.